Well, I think everyone's here, so we might as well get started. Welcome back. Thank you all for coming to the other room. I think I kind of like this room a little bit better, but I hope that you can see the screen all right. Is there glare from the windows? No? Great. There's one back there too, if you really want to look at. That one has some spots on it. I'm not sure what's up with that. I did record and post the video from last time, so you can go check it out. Like and subscribe if you want. Let's talk some more about the u-substitution. I had a few more examples to do, and then I got some for you all to try, and I'm going to come around and see what you think. And then we'll get on to the next, the next topic. This u-substitution thing I still consider to be review. I hope that this is something that you've all seen before. Let's just do another one. How about, so one thing we didn't do one last time that has the little numbers in there, so we'll try one like that. I'm going to do x times 3x squared plus 5 to the power 10 dx. All right, so the fact that there are some little numbers here doesn't really make much of a difference. We will just try and proceed as usual. We'll deal with the numbers when we have to. Our first step should be to try to choose part of this to be the u. Anybody got a suggestion? Yep. 3x squared plus 5, she says. Great. That is the inside of the parentheses. If you see inside of parentheses somewhere, that's typically a good bet for what you want to choose the u to be. Then the next thing you should do is figure out the du. The du is always the derivative of the u, which in this case would be 6x dx. So remember, the du is always the derivative of u and then times dx. Dx is always included as part of the du. All right, and now we are going to try to substitute stuff in. Actually, I'm going to divide the constant here. This is the old divide the constant trick. This 6, it will be more convenient to write the 6 on the other side as a 1/6. So I'm going to say 1/6 du equals x times dx. That's what I call dividing the constant. This is usually necessary in order to make this work, at least the way that I write this. Some of you may have learned, sometimes when people teach this, they say you should multiply and divide by 6 in this formula first to make this work out. You can do that if you know what I'm talking about. You can do it that way. If not, I think it's easier to divide the 6. Anyway, now I'm going to try to plug all this stuff in where it goes. Just like last time, I'm going to write this in a few sort of intermediate steps. And I'm also going to temporarily ignore little numbers 1 and 4 for now. So I'm going to write, first of all, just stick the u where it goes. U to the 6, it should be 10. That part inside the parentheses is u. And so I'm going to plug that in exactly where it is. Right here, this is the u, so it's now u to the 10. And then I also want to substitute for the x and the dx. We need to somehow change those into something involving u's, but if you look over here, you can see x times dx is 1/6 du. So if you like, you could write just one little intermediate step, which is not necessary if you want to do that step in your head. It is u to the 10th times 1/6 du. All right, I hope everybody's feeling okay about that. U to the 10th times 1/6 du. And then I'm going to, we still haven't done the integral, right? There's still an integral sign there. Let's move the 1/6 out of the integral. You can always factor a constant multiple outside of an integral sign, just to simplify a little bit more. Sorry, not dx, du. And now the thing is simplified enough to actually do the integral. So we're going to do the antiderivative. That's when you increase the power by 1 and then divide in front by the new power. So u to the 10 will become u to the 11, and I have to divide by 11. So it's going to be 1/6, which was just from before, 1 over 11, u to the 11. 11. And now, I'm not going to put the plus c. I'm not going to put the plus c because now we have to deal with the numbers, 1 and the 4, right? But this is the antiderivative. All right, everybody satisfied so far? I hope so. If you want to multiply, 6 times 11 is 1 over 66. That's fine. I don't really care about that. All right. Now, to plug in the numbers, instead of the plus c, of course, we have to plug in the numbers 1 and 4. You don't want to plug in 1 and 4 directly right here for the u, though, because these 1 and the 4 from the beginning, these represent values of x that should be plugged in. So before plugging the 1 and the 4, we need to replace the original variable, which is x. This usually we do as the last step anyway, so let's do that. The last, well, it's not quite the last step this time, but I'm going to put x's back in instead of u. So it says now 3x squared plus 5 to the 11. That is just right here. This is what u is. U is 3x squared plus 5. So u becomes 3x squared plus 5. And then finally we can plug the values in at the end and get our final answer. So here I'm going to put the bar 1 and 4. These are x values. You don't want to plug 1 and 4 in right here for u. You have to plug them in for x, which will give you it's different. You'll get a different answer either way. So do it right. All right, so I get 1 over 66, and here 3 times 4 squared plus 5 to the power 11. And as usual, I don't really care what that is. If you really want, you could plug it into your calculator. Minus, same thing, but plug in 1 for x. 1 over 66. 3 times 1 squared plus 5 to the 11. There we go. This is my final answer. Did I mention, it said on the syllabus, no calculators on the tests. Did I say that? I don't know. It definitely said that in the syllabus. I don't know if I said it. On our tests or whatever, I would expect you to just leave your answer looking like that. You shouldn't try to simplify that anymore. Of course, you can if you want to, although without a calculator, you're liable to screw it up anyway. All right, any questions about that one? Great. I said I had 3. Let's do 2 more, and then I got some for you all to try. So the next 2 are slightly weird in that it is a little less obvious how you should choose the u. So here's 1 sine x divided by cosine to the 4x dx. A bit less obvious about how to choose the u. In this example, because I don't see any parentheses, like I have always in the past said, you should just like choose something which is on the inside of parentheses. But I don't see any parentheses in this case. Instead, we see a fraction. In this case, I would say we should maybe rewrite this a little bit. It's not strictly speaking necessary. Although this down here, cosine to the 4 of x, I hope everybody remembers what that means. That means cosine of x, the whole thing to the 4th power, right? So just to clarify a little, cosine of x to the 4, right? I actually don't really like how people write things this way. This is totally like standard. Everybody writes it like that, although I think it's a little confusing. To me, this looks like 4 cosines and an x, but that's not what that means. It means cosine of x, the whole thing to the 4th power. All right. Anyway, now that you write it this way, maybe it becomes, at least now there are some parentheses somewhere. So I'm going to take the u to be just the cosine of x. Now there's a lot of other stuff going on here, but hopefully everything will just kind of work out. I'm going to take the u to be just cosine x. And hopefully the other stuff is going to work out okay. All right. Anyway, from here, what do you say? Can somebody say what's the du in this case? Yes. What do you say? Yeah, du, remember, is always the derivative of u. In this case, it is negative sine x. I cut her off before she could finish. Dx. Negative sine x dx. You always keep the dx as part of the du. All right. Excellent. Yeah, okay, great. I would often divide a constant. Like in the previous example, there was like a 6 here, which I moved to the other side. We might as well do that here. We have a negative sign here. I'm going to move that to the other side. Minus du equals sine x dx. I don't know if that's really going to be helpful, but maybe it is. Okay? And let's try to do the plugging in. So over here, I am going to start substituting. Now, usually I like to just as a first step, just put the u where it goes. So u is cosine x, so that goes right here. So this is going to say integral sine x over u to the power 4 dx. All right. So I put the u in. What remains here is a sine x and a dx. And actually, like at this point, you should start sort of looking over here and trying to say, do you see the whatever the leftover stuff is here? Do you see that as part of the du? And I think I do actually. This is sine of x and dx is right here, sine of x dx. So I'm feeling pretty good about this. Maybe just to make this look precisely the way I want, you could say this is 1 over u to the 4 times sine x dx. That's because like this fraction, you know, sine of x over u to the 4 is the same as 1 over u to the 4 times sine of x, right? That's just another way of writing this fraction. But now you can see sine x dx is all together, and that equals negative du. So we get 1 over u to the 4 times negative du. And as usual, I am going to factor the constant out. That minus sign you could think of as like a multiplication by -1. So we can take that out of the integral. Minus integral 1 over u to the 4 du. And now this is totally substituted, right? Everything is now in terms of u rather than x. And so we should do the integral. Anybody want to suggest? This is still you have to think a little bit. How do we handle this kind of a thing? 1 over u to the 4? Any ideas? It's a fraction, which makes it slightly complicated. You cannot just leave a fraction and do the antiderivative on the bottom. Yeah?
U to the negative?
Yeah, you should write this using a negative exponent because 1 over u to the 4 is the same as u to the minus 4. So I am not doing the integral yet, but just rewriting what's on the inside. 1 over u to the 4 is the same as u to the minus 4. And now we can do the integral finally by doing the thing with the power. You increase the power by 1, and then you divide by the new exponent. So I'll leave my minus sign out there, and then it's increase the power by 1. The power now becomes u to the minus 3. And then I divide by this exponent, so I put a 1 over minus 3 in the front. And then a plus c. It's a plus c this time because there's no little numbers to plug in. We just do with a plus c. Right. And there's one last step, and remember the final, the cherry on top, as it were. Yeah?
Plug it in for x.
Yeah, put the x's back in. Since the original integral is in terms of x, you should write your answer as a function in terms of x. So that's always easy to do. You just replace u is cosine x. So this, I'm going to, would you mind if I cancel those two minus signs? It's just 1/3, and then cosine x to the minus 3 plus c, the end. All right, I hope that one makes sense to everybody. I thought I'd mention, I haven't mentioned this yet, but all of these integrals with the u-substitution, or really any integral trick that you're going to use, you can always check your answer if you got time on the test or whatever. This is a good idea to check your answer. Anybody know how would you check this answer to make sure that you did it right? This whole problem is about an antiderivative something. Yeah, you can take the derivative of the final answer, and if you did it right, you should get this when you take the derivative of that. Can we just try and do that? So let's try and check it. You should take the derivative of the final answer, and if everything is correct, what you should get is the thing that you started with on the inside of the integral sign. So I'm going to do derivative of 1/3 cosine x to the minus 3 plus c. What do we get? For this kind of a derivative, you will need to do the chain rule because I have cosine inside of this power. And I hope you remember this constant coefficient doesn't make a difference. You might worry about, do I also have to do the product rule because it's a 1/3 times of this thing? It's true, it is a 1/3 times that thing, but since it's a constant in the front, you don't need the product rule. You just leave the constant like it is. So when I do this derivative, the 1/3 stays like it is, and then I do the derivative of the rest of it. The exponent comes down to the front, Then I decrease the exponent by 1, like that. So this is the derivative of the cosine x to the -3 part. And then, because I'm doing the chain rule, we additionally multiply times the derivative of the inside of the parentheses. And that, in this case, would be negative sine x. So this is from the chain rule. It's the derivative of the inside. Derivative of cosine is negative sine. And then plus c, you take the derivative of that, and it disappears because this is a constant, and the derivative makes it become 0. All right? Is that really, I said, ideally, if you did everything right, this should equal what you started with on the inside of the integral sign. Now, it doesn't look the same yet, but actually it is the same. If I cancel, I can cancel the 1/3, right? This 1/3 and the 3 cancel, and then I have this minus sign, which can cancel that minus sign over there, here and here, right? Those can cancel because it's all multiplied together. And so all that's left over, if you simplify here, is sine x times cosine x to the -4. And of course, the negative power is the same as writing that thing in a denominator. So this is the same as sine x over cosine x to the 4. And that really is the same as what we started with. So I say check. I checked it. All right. Good thing to do if you got the time on the test or whatever. You can always, whenever anyone asks you to do the integral of something, you can always check the answer. All right. Excellent. Let's try. I said that was 2. I said I had 3, and then I got some for you to try. The third one is actually a little tricky. These ones that we've done so far, I would consider to be more or less ordinary sort of routine ones. I'm not saying it's easy, but the u-substitution is often sort of a tricky thing to get straight. This next one is a little outside the box, though. So here is, I will say, a fancy one. Here's a fancy one. How about integral x times root x plus 1 dx? All right. I don't know if this looks like anything special. I think this is one of those things you don't really realize that it's a fancy one until you really get into it. So let's just try and do this, not worrying about the fact that I said this was a fancy one. Anyone want to suggest? Well, how would you choose the u if you didn't know any better? Yeah?
I would put the x plus 1 in the square root in parentheses and then just switch the square root to like a 1/2 exponent and then use x plus 1.
Yeah, great. So it's always a good idea in this class to write square roots as 1/2 power. It is basically never helpful to write things using the radical sign. All right, so yeah, think of it this way first of all. And then she said, choose u to be the inside of the parentheses, which is a great idea. And this is not a trick question. I mean, this actually is the way to do it. What makes this a fancy one is what's going to happen sort of in the very next step. All right, so that's a good choice for the u. Now we write the du as usual. Can anyone say what's the du in this case? Yeah? Yeah, 1. By 1, I'm sure she means 1 times dx, right? You always have to put the dx there, remember? So this is just, can I just say dx, right? 1 times dx if you like, or just dx. Okay, what's next? Now we try to make the substitutions. So as usual, I would begin by just putting the u where it goes. So this will say x u to the 1/2 dx, right? And now is the point at which things have to get a little fancy. I see x, u to the 1/2, and dx. Now sometimes I like to just kind of gather together. I write the u to the 1/2 first, x times dx. And what I always say is, okay, let's look at the leftover parts. And do I see this over here? And in all previous examples, this part has just matched the du, or maybe I have to divide the constant or something. But in this case, it doesn't, right? Here I have x times dx, but the du is just dx. And this is a problem, right? Dx, you could replace this dx by du, but you are left with an extra x here. And how are you going to change this extra x into something involving u's and du's. All right, so the big question here is what to do with x, just x by itself. See, this dx I can turn into du because dx equals du. So if you like, you could say this is u to the 1/2 times x times du. That's just because dx and du are the same thing. What? They're telling me to. Software update. Not now. All right. What about the x? Anybody done a fancy one like this in the past? Any ideas? This is slightly out of the box here. What about the x? What we usually do is we look over here and say, you know, do I see something about x times dx? Like you don't in this example. There is nothing about x times dx. You can, though, express x in terms of u from this one. So this is another kind of trick which we have never had to do in the previous examples. You can solve that one for x, and it's not hard to do. U equals x plus 1, so I can say x equals u minus 1. And that is what you can do with the x. Remember, your goal in doing these substitutions is to change all of the x's into u's somehow. And this is how you can do it. If x equals u minus 1, then this right here can become u to the 1/2 times, make sure you put these parentheses there, it matters, x equals u minus 1. This is a weird step that usually you don't have to do, but sometimes you do. X equals u minus 1 in this case. All right. Now we have changed everything into u's. The issue at this point is now this thing is not all that simple. Like this integral here has a multiplication in it. So we'll have to think about, is there some way to handle this multiplication? You cannot just do the integral of this part and also the integral of this part, of course. Any ideas how we could maybe rewrite this, simplify this somehow so that you could do the integral? The problem is really the multiplication. I don't like multiplication inside the integral sign. Got an idea?
Distribute the u to the 1/2.
Yeah, here we can distribute. So I'm going to do like so, right? And when you're distributing powers of u, you would be adding the exponents, right? So this u by itself is like a u to the 1. So I should add the exponents 1 plus 1/2. That's, 1.5, 3/2. So this, when I distribute, becomes u to the 3/2, and then minus u to the 1/2 times 1 is u to the 1/2. And now we are ready to do the integral, right? This is just two powers added together, subtracted, whatever. And we can do the integral with the usual rule about the power. So we increase the power by 1, etc. So this u to the 3/2 becomes u to the 5/2. That's 3/2 plus 1. Which is 3/2 plus 2/2, which is 5/2. And then we divide in front 1 over 5/2, or if you prefer, I kind of like doing 2/5, right? That's the reciprocal of 5/2. Or you could write 1 over 5/2, whatever. And then the other one, similar, minus. This is going to be a 2/3 u to the 3/2. And then I put the plus c. All right. And then finally, as always, we replace the variable with x's. So looking way back at the original solution, u equals x plus 1. And so my final answer is 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2. The end. Right? As always, you could check your answer, although I don't think we need to go through all of that. Anybody got questions about this one? This, in my opinion, is a tricky one. It involves, the tricky part is just doing this extra little step here. I mean, it's not really a hard step. It's just you have to recognize how to do it. All right, I got 3 for you all to try. Where? Oh, here. Let's try, and I'm gonna, like I did yesterday, I'm gonna walk around and see how you're doing. I'm here to help. How about integral 0 to root pi x sine of x squared dx. And integral like so. And like so. All right, see what you think. Feel free to chat with your friends and neighbors about it. I'm going to come around and see how you're doing. Yeah.
Am I doing answer for this?
Yeah, it looks great.
Can you just replace the did you write the two dx there or no? Like if you're plugging that in for the du.
Not quite. I think it's kind of backwards. So this, you replace dx with this, but it's this thing is du.
Oh, so it's just du.
No, I mean this is.
Oh, this.
Yeah, this is what you want to use. So I would say move this x over here. So the x goes with the x. And then the next step. So don't put x there. Sine of u, yeah, and then x.
Yeah.
Because that's just like this guy. These are multiplied, so you
Oh,
can
and
do
then
this
it's
one.
that. And this
So
is
this part becomes, yeah, right. That's a u on that side.
and then you just rearrange.
Yeah, exactly.
Okay,
Yep.
thank you.
You good here?
Yeah.
Yeah, that's it. That's all right.
Yes, I think so.
Think so. Don't forget this 1/2.
Can you?
What were you thinking?
Yeah.
Yeah, this, if it's a multiplied constant on the inside.
We can just write that, okay.
Okay? Looking good? Nice, everyone, this two, when you put it on the other side, you were dividing it, like you're really dividing this side, like you said.
Got it.
Good here? Yeah, good, looks great. The integral of sine is
Yep.
so the minuses. Yeah, looks great. Okay. which it says sign of you. If you do it here, the sign here,
Oh,
they
okay.
should be
Okay.
together. But then this is correct.
Okay.
So it should really, actually this is all good except this right here. It should say sign you. Mm-hmm. This is good so far. Do you remember what we did at similar steps in the previous ones?
I tried to read that.
Yeah, so it's kind of like here, you have some stuff with U's and some extra constant in there. The next step here was you can pull the constant out of
Yeah.
here. And then from that, you actually do the integer.
So then you take, like, then you take.
So take the 1/2 out to the front. Mhm. Right, and now you should just do the integer of that. You okay? Yeah, yeah. That's good. Still good here?
I'm just. What's
Mhm. Yeah. You have to do some slightly weird tricks for that one. Still doing all right? Yeah. Still good. Yeah, it's looking good. Still good here? Your last step should be to put that. It's always easy to do, but, and there should be a plus here. Still doing all right? This is. Oh, you're trying to do something fancy with this. It's too complicated. Right here, x times dx. It's just that. Which is a lot of like this is also, it's not wrong, but it's makes everything else too complicated. Like actually, once you put that here, then this step is wrong because you have multiplication. You can't just do the integral on both parts.
So I didn't have to do like.
Yeah, this extra thing is not necessarily this wrong.
Thank you.
Yeah, it's not necessarily wrong, but it makes it so wrong. So just x dx, just make it 1/2 cubed, and then this becomes a lot simpler. Still good? Fancy one here. Yeah, yeah, that's right. Still good here? Yeah, I think so. How's it going? Alright, that's a good choice for the U. Still doing okay? Still good?
Oh, I forgot to write
You
it.
forgot the sign.
Yeah, I forgot to write that.
So then when you do the integral, it's
Yeah.
still different. Still good here? Mm-hmm. You should, just the last step, I should need to put that.
Oh, okay.
That's easy. How's it going? You work out the other one?
Yeah, I think so.
Yeah, that's good. Yeah.
Am I doing this one? It's okay.
Good so far, yeah.
So it's like the, I was gonna focus on the steps, like what do you do next after this one?
So there should still be a dx there. I would say to, what I like to do is kind of separate out. It's similar to this one, where there's a fraction. I turn it into that and that. So see if you can do something like that.
Oh, I see.
So Sort of pull apart the fraction. Yeah, as it 1 over something times. Great. You good here? Yeah. Still good?
Yeah, I think so.
That's a good choice for the U.
Okay.
How's it going here? This is
Second
good so far.
Yeah, like.
This one you have to do a slightly weird step.
Rearranging these.
Things weird about this. Sorry, no, it's okay. I thought maybe it would happen. Yeah, so you have to be a little cute about, this is one of those ones where you're gonna rearrange this. You can kind of solve this for x squared instead of b.
Okay.
You're gonna plug that in over here.
And what X?
Yeah, this is x cubed. So if you think of this x cubed as a x squared and also a x,
Okay.
the x squared you can add this and the extra x.
Okay.
A little tricky. Let's take about 5 more minutes and then we can go over these. Still doing all right here? Sorry. Still doing good here?
It's like uncomfortable.
It's fine. Yeah. Great. Still doing all right here? I'll go to the hard part. Yes. This is good? Yeah. You're all good so far. What's weird is that's x squared, but that's x cubed. But you can. How's it doing? Yeah. This is good so far. I would split it apart. So write it as 1/4 times x squared. And then of course you have dx. So now what do you do with x squared and dx? That comes from here. You can divide the 3 to the other side. And then what do you do with 1 to the 4? That was a 1. Still doing okay? Yes. So the sign when you do the inverse.
So that just becomes x squared, and then I just found x squared. And then I just got u minus 1 squared.
That's because whenever you do the integral of anything, you do the integral of the function, and then you don't want to use the sign anymore. You don't want to use the sign. So this should just go. There should not be squared. All good? Yeah. That was good. There should probably be some. And technically there should be parentheses around that, because the 1/2 would be in here, the 1/2 goes
Yeah.
on the outside. Okay. Doing good here? Yeah. Excellent. How's it going? That's a good start. And this looks pretty good. Great. I'll give you 2 more minutes. How's it going?
Good, I'm just stuck on.
This is good? Yeah, so this is one of those ones you have to do this.
Yeah.
So you can, I would say, solve that for x squared.
Okay.
Instead of x squared is minus 1.
Mhm.
And then that squared, you get this, and the extra x.
Oh, okay.
How's it going?
I was trying to listen to
Okay.
him.
Yeah, this is the hard one, I would say.
So you're saying like use the x squared if you like factor out it here?
Yeah, this x cubed, you think of as the x squared times the x. And the x squared part is that, becomes that.
Right.
And the x part is like this.
Right here.
X times dx.
Okay.
Yep. Let's see if we can that one.
I used that instead of.
So I like this. I like the mix.
I just,
You did not need the derivative.
Yeah, I did the derivative.
You have to, you have to deal with this multiplication. When you're doing an integral.
Okay.
Welcome. We're in the middle of class.
Oh, then we're early for
Yeah,
class. I'm so sorry.
Sorry, you can hang out. We got 10 minutes left.
Sorry.
You should distribute here. and-
Okay, okay.
All right, let's talk about these so that they can get their seats back. I would, in my opinion, these are kind of like in increasing level of difficulty. The first two are fairly straightforward. The last one involves some slightly weird tricks. So let's try the first one here. We are going to do the substitution u equals x squared. That being the inside of the parentheses. Then the du is 2x dx. And I'm going to divide the 2 onto the other side, just because that is usually helpful. 1/2 du equals x dx. And then I go to plug stuff in. It says x and then sine of u dx. I just put the u in for x squared. And now I have to think about how to handle the extra x left over and the dx. It becomes clear if you write them sort of together. I'm just going to rearrange the ordering here. Sine of u times x dx. And now I see x dx up here is 1/2 du. So this is integral sine of u times 1/2 du. Pull the 1/2 out to the front. I'm doing this quick just because pretty much everybody did this great already. 1/2 sine of u times du. And then we do the integral of the sine of u. So this is 1/2 sine of u. The integral is negative, so this is times, minus cosine of u. I was about to write the plus c, but actually we have numbers to plug in. Remember, you should not plug those numbers in at this point. For u, they are values of x. So before plugging the numbers in, I have to replace the original variable of x. I'm going to write minus 1/2 cosine of x squared. And then plugging in 0 and root pi, all right? Instead of u, I use x squared, which is the original variable that u was substituted for. Okay, plug these in. I got minus 1/2 cosine of root pi squared minus 1/2 cosine of 0 squared, all right? If this one was on a test or a quiz, I might say simplify all the trig functions in your answer. I would expect you to know how to do sines and cosines of the standard values around the unit circle. So here, if I wanted to simplify fully, ordinarily I wouldn't try to simplify anymore, but I might tell you to in the case of the trig functions, because I want to make sure that everybody knows the values. Cosine of root pi squared. First of all, root pi squared is pi, because the square and the square root cancel each other out. So this is cosine pi, and then the next part says plus 1/2 cosine 0. I simplified the minus and the minus. And I hope everybody remembers, cosine of pi is -1, so this is minus 1/2 times -1, plus cosine of 0 is +1. And so this is just 1/2 plus 1/2, which is 1 altogether. It's a lot of work just to get 1, but that's how we do it. Any questions about that one? I hope it worked out. I saw, slight variations on this. Everybody seemed to be more or less on the right track, though. Okay, next. The fraction one. Bring it down. All right. So this one, to choose the u, you should, again, just choose the inside of the parentheses that you can see there. So it's 1 minus x cubed. then the du is the derivative of that will be negative 3x squared dx. And I feel pretty good about this because this has an x squared in it, and I also see an x squared over here. Now, in order to sort of rearrange stuff to make this work out, I would begin by plugging u in the denominator there, u to the 4 on the bottom, dx. And then split apart this fraction. So you can write 1 over u to the 4 times x squared dx. This is how I would typically write it. You may prefer, I know some people like sort of go into negative exponents. Another way you could do this is just writing, instead of 1 over u to the, like u to the 4 on the bottom, you can write that as a negative power, u to the minus 4x squared dx. Actually, these are the same, right? It's just a matter of how you want to write it. Okay, anyway, to continue the substitution, x squared dx, coming from here, I divide the 3 over to the other side. Negative 1/3 du equals x squared dx. And so this becomes integral u to the minus 4 times negative 1/3 du. And then we can move the constant outside of the integral sign, and everything is all ready to do the antiderivative like that. All right. Now sort of the hard steps are over at this point. From here, it's just a matter of doing the antiderivatives. I hope everybody is with it up to this point. We do the antiderivative, increase the power by 1. Well, leave this guy out front, right? And now increase the power by 1, it becomes u to the minus 3, and then divide by the new exponent. That would be 1 over minus 3. And I'll put the plus c. That, if you like, you could say is 1/9 on the front. U to the minus 3, we should write our final answer in terms of x again, and so it will be whatever the x was, 1 minus x cubed to the minus 3. There you go. That's what I got. Any thoughts about that one? I think most people worked this out as I was going around. I hope so. All right, and let's try the last one. The last one is the hardest one, I would say, maybe by a long shot. It involves a weird substitution, slightly weirder than the weird example that we did before. But anyway, you should begin by choosing the u to be the inside of the parentheses, x squared plus 1, and then make the du as you usually would. It would be 2x dx. You can divide the constant as I usually would, 1/2 du. Whoa. 1/2 du is x dx, right? And then try to plug this stuff in. And here's where things get a little messy. It becomes x cubed u to the 10 dx, all right? And this is the point, and maybe just because I usually like to write the u's first and gather together the x's that are left over. This is the point at which you will sort of hit a what looks like a dead end here. The reason that this looks like a dead end to me is what I have left over is x cubed dx, but the du is just x dx. How am I going to handle, I mean, it doesn't match, right? Ideally, you want this to match with this. Anybody, I saw some people got this far. What did you do to work it out?
So if you were to substitute it anyway, you'd be left with x squared because the x and the x would cancel out.
Yeah, so this is one good observation. When I'm trying to match these up, this, like, I guess part of it matches with this, right? This is x cubed, which you could think of as an x squared times a x. So as one sort of baby step here, x squared times x dx, right? And x dx, I already know how to handle that. How do you handle x squared? What'd you say?
Just isolate it in u equals x squared plus 1.
Right. So this x times dx, and this is a non-obvious step, so that's what makes this one a hard one. This x times dx comes from there. This x squared is handled from here, u equals x squared plus 1, and like she said, you can isolate the x squared from that. So this becomes, sorry for all my arrows, looks like a crazy person wrote this. X squared equals u minus 1, right? That's what she said. Isolate the x squared there. And so when we plug in, the x squared part becomes u minus 1. The x dx becomes 1/2 du. And this is the hard part. x squared becomes u minus 1. And then x dx becomes 1/2 du. All right. Now we have to work a little bit more just because we still have a product on the inside here, which is generally no good. We can remove the 1/2 as we would usually do. That's not a problem. But what is a problem is this extra multiplication on the inside. Anybody see how to handle that? I'm referring to this multiplication right here. You cannot just do the integral of this and also the integral of this. What'd you do? Huh?
Just distribute the.
Distribute it, yeah. This guy distributes here and here. So it becomes, oh, it's time to go. We're just about done here. U to the 10 times u is u to the 11. Sorry, integral. I'm not doing the integral yet. U to the 11 minus u to the 10 du, right? And now finally we can do the integration by changing the exponents. So it's 1/2 1 over 12 u to the 12 minus 1 over 11 u to the 11 plus c. And then the very last step, you put the x's back in. So 1/12, make sure those parentheses are there. They matter. 1/12 u is x squared plus 1 to the 12 minus 1/11 x squared plus 1 to the 11. There you go. That's a hard one, in my opinion. All right, this is pretty much all I want to say about u-substitution. So you'll have some practice with these on the homework, and they will be on the quiz next week. So next time we'll do something different. Back in the other room.